Welcome to another Explainer. I'm your host, and today we're diving into something that honestly feels straight out of science fiction, but it's actually a highly accessible, open source tool. Just imagine giving a computer a natural language command, just a simple action instruction, and having it instantly predict 3D pixel trajectories in real time. Pretty wild, right? Well, that's exactly what we're unpacking today as we explore the newly released MolmoMotion repository from Allen AI.
Okay, here's our roadmap for today. First up, we'll officially meet MolmoMotion, then we'll walk through the setup and datasets. After that, we'll break down the two-stage training process, check out how to evaluate it with metrics, and finally, wrap up with a really cool real-world robotics application. So let's jump right into part one, meeting MolmoMotion, this brand new vision language model. Imagine being a movie director, right? You're on stage giving actors 3D blocking instructions, telling them exactly where to move and how to interact. Now imagine doing that, but for pixels, and eventually for robots. That's MolmoMotion in a nutshell. It's a vision language model that takes a super short history of RGB video frames, some 2D query points with their starting 3D positions, and a plain English natural language action description. Then it fuses all of that together to forecast exactly where those points are going to move in 3D space. And just to put things into perspective, we are working with some massive scale here. A 4 billion parameter model is acting as our autoregressive backbone. So yeah, this isn't just some lightweight toy script. It's a really hefty, highly capable model that fundamentally understands both complex spatial relationships and language instructions at the exact same time. The really crucial takeaway here is that this massive model can predict the 3D trajectory of each query point for up to 2 seconds of future motion, running at 15 frames per second. And it does all of this in the camera's coordinate frame from the very first time step. Now, I know 2 seconds might sound incredibly brief, but trust me, in the fast-paced realm of robotics and precise video forecasting, being able to accurately anticipate the next 2 seconds of 3D movement, that is an absolute game changer. Moving right along to part two, let's look at the setup and datasets to build our foundation. Getting this up and running in your own local environment is actually surprisingly simple if you just take it step by step. First, you'll need to make sure your PyTorch version perfectly matches your specific CUDA driver, and you'll want to grab FFmpeg for system video decoding. Second, you're going to download the training corpus, that's MolmoMotion 1M, along with the evaluation suite, PointMotionBench, straight from Hugging Face. Finally, just run the provided Python quick start script. But listen, there's one golden rule you need to remember. Always point your dataset roots to new directories entirely outside the GitHub repository. Otherwise, things are going to get real messy real fast. Also, a quick heads up for all you developers tackling this pipeline. When you download from Hugging Face, you're really only getting the annotations, tracks, and camera data. Because of licensing restrictions on the original source videos, you absolutely have to run the local reconstruction scripts provided in the repo to get the actual raw MP4s. Seriously, don't skip this step, or your data pipeline just flat out won't work. Now, let's compare the two autoregressive models they've released just so you know exactly which weights to pull for your project. First, there's the H3F30 variant. This one uses 3 history frames to predict 30 future frames, making it your absolute go-to for typical video applications. Then, on the flip side, we have the H1F32 variant. This one relies on just one single history frame to predict 32 frames into the future. That makes it absolutely perfect for scenarios where you only have a single query keyframe to kick off the movement. Okay, let's shift gears to part 3 and look under the hood at the two-stage training process. Think of this as your fuel. We've got 5 human video datasets used in the public training mix: EgoDex, YTViz, HD Epic, Experience, and Stereo 4D. And what's really clever here is that they use a square root frequency mixing strategy. Basically, this ensures that the massive datasets don't completely drown out the highly specific smaller ones. It gives the model a perfectly balanced diet of diverse 3D motion scenarios to learn from. But hey, before you launch your training run, there's a vital bit of housekeeping. You have to build the track keys cache using the script they provide. Why do we care about a track keys cache? Well, mostly so your model doesn't just randomly crash mid-training because of missing files. This is super crucial for datasets like Stereo 4D that actually require local track rebuilding. So do yourself a favor, run the script, cache the keys, and save yourself a massive headache later. As for the training itself, it happens in 2 distinct autoregressive stages. Stage 1 is a pre-training phase that spans 40,000 steps. It starts off small, using 8 points, a history of 3 frames, and predicting just 8 future frames. But then Stage 2 steps in for a 10,000-step long horizon fine-tune. This is where the model really stretches its predictive muscles, extending those future frames out to 30 or 32 and smoothly transitioning from those short bursts into that impressive 2-second forecasting window we talked about.
Moving on to part 4, evaluation and metrics, or basically how we keep score.
So, how do we actually measure forecasting success in 3D space? Evaluating the PointMotionBench benchmark across highly varied datasets like HO3D, WorldTrack, and Davis requires some rigorous yardsticks. We can't just eyeball a 3D trajectory and call it good, right? We need hard mathematical proof that our natural language instructions are translating into accurate physical physics.
To get that proof, we use 3 metrics that complement each other to give us the full picture. First is ADE, or average displacement error, which looks at the entire journey. It measures the mean error across all predicted time steps. Then we have FDE, the final displacement error, which strictly looks at whether we hit the bullseye at the very end of the sequence. For both ADE and FDE, lower numbers are exactly what you want. And finally, there's PWT, or points within threshold. This measures strict accuracy thresholds in meters, basically calculating the fraction of points that landed exactly where they were supposed to. For PWT, you want that number to be as high as humanly possible. Oh, and one super important technical note if you're running these evaluations yourself. The default evaluation script in the repository uses a greedy, deterministic best-of-1 decoding method. But if you read the official paper, you'll see they report numbers based on a best-of-5 decoding strategy. Don't worry, though, you can easily reproduce the paper's numbers just by tweaking your sample flags to 5 when you run the eval script. Let's head into our final section, Part 5. This is the grand finale, seeing a real-world robotics application with MolmoBot. Guys, the real-world payoff here is absolutely huge. This repository doesn't just stop at video forecasting, it literally gives you a full recipe for robotics. By taking this learned 3D motion prior, which, remember, was trained purely on human videos, and using it to initialize a MolmoBot manipulation policy, you can apply it directly to the MolmoSpace's Franca pick-and-place benchmark. It is quite literally a stunning bridge from digital pixels straight to physical robotic actions. And that brings us to the end of our journey today. I want to leave you with this thought. The repository is completely open, the weights are available, and the blueprint is laid out right in front of you. So whether you're tinkering with some wild new video generation pipeline or you're writing planning policies for a robotic arm, the tools are literally right there in your hands. The only question left is, what are you going to build with it? Thanks so much for exploring this with me today, and I'll catch you on the next explainer.